So next what I want to do is find the Laplace transform of t to a power. And if we do that, let's just kind of track what's going to happen here. We're going to do integration by parts again. And I just want to see what we're going to get here. So this is going to be, we're going to do integration by parts. We're going to, let's see, I want to differentiate t to the a, so I want to anti-differentiate e to the negative st. So this will be negative 1 over s, e to the negative st, t to the a, so as t goes from 0 to infinity. Let's see, then that's going to go from 0 to infinity, and then minus the integral from 0 to infinity. Let's see, we have a negative 1 over s, e to the negative st, times the derivative of t to the a, which is a t to the a minus 1 dt. Okay, and let's see how this is going to work. We're going to end up with, let's see, as t goes to infinity, this is going to be 0. And as t goes to 0, this is going to be, we need to be a little bit careful here, but as t goes to 0, as t goes to 0, that e to the negative st is going to be a constant, and so t to the a is going to be 0, unless a itself is 0. So this is going to be minus 0. So let's, for now, let's say that a is positive. If a is 0, we know how to do those anyways. So this is really going to be most useful when a is positive. So let's see, we're going to have, this is going to be 0 plus a over s times the integral from 0 to infinity e to the minus st times t to the a minus 1 dt. Okay, and so what happened was we saw that the Laplace transform of t to the a was, so the integral from 0 to infinity, e to the negative st, t to the a, dt, and that was a over s, times the same integral from 0 to infinity, e to the negative st, just t to the a minus 1 dt. Okay, and so if we do this over and over and over and over again, let's do this for t to the 4th, just to make sure that we get it. So this means that a is 4. So we're going to have the integral from 0 to infinity, e to the negative st, t to the 4 dt. Turns out that that's going to be 4 over s times the integral from 0 to infinity, e to the negative st times t cubed dt. And then we can do this again for t cubed. This is going to be, so let's just copy down the 4 over s times, let's see, we're going to have times 3 over s, integral from 0 to infinity, e to the negative st, t squared dt. This feels a little bit like the gamma function, right? And there's a reason. This is going to be, so I'm just going to leave it as 4 times 3 over s squared. And then I'm going to look at the integral of e to the negative st t squared. And that's going to be 2 over s, integral from 0 to infinity, e to the negative st times t. And altogether, this is going to be 4 times 3 times 2 over s cubed times 1 over s, integral from 0 to infinity, e to the negative st, t to the 0 dt. And that's going to end up being e to the negative st. If we integrate that, it's going to end up giving us, that's the Laplace transform of 1. So that's going to be another 1 over s. So this is going to end up being 4 factorial over, this is s to the 4th out here. So just to be clear about where everything's coming from. So that's 4 factorial over s to the 4th. This integral from 0 to infinity, e to the negative st dt is 1 over s. So it's going to be another 1 over s. Okay, and altogether that's going to end up being 4 factorial over s to the 5th. And so it turns out that what's going to happen is if you have t to the n, where n is an integer, so if n is an integer, then the Laplace transform of t to the n is going to be n factorial over s to the n plus 1. And it turns out that this is, if you remember about the gamma function, you should go back and watch the video on the gamma function if this fact is not fresh here, but this is gamma of n plus 1, right? In other words, remember that, just recall that gamma of n is n minus 1 factorial, right? So 4 factorial is gamma of 5, and so on. The reason why I write this like this is that it's actually true that the Laplace transform of t to the a is gamma of a plus 1 over s to the a plus 1. That's actually true whether or not a is an integer. So if a is really any real number there, this is true. And actually this version of this holds. This holds if a is strictly bigger than negative 1. So for example, if we were to look at the Laplace transform of 1 over square root of t, that's the Laplace transform of t to the negative 1/2. And that's going to turn out to be the Laplace transform, or that's, the gamma function of 1/2 over s to the 1/2. And gamma of 1/2 is square root of pi. So this is square root of pi over square root of s, or if you like better, you could write this as square root of pi over s. This is only valid if s is positive, so we need a to be greater than negative 1, and we need s to be positive just in general. So that's how we'll find the transform of powers.